Turns out my video just stopped there, so it's actually not bad. So what we were talking about is, now we're going to talk about the force, right? So from here down, talking about the force magnetic, okay? And we're talking about the force magnetic on a moving charge, all right? So as I was saying before, it's important to understand the direction of this field, okay? And the direction of the field in here and things like that, okay? Because those fields, B, apply a force magnetic on a charge with a velocity, okay? And here, this sign is going to tell us the angle between the field itself and the particle's velocity, all right? So let me go ahead and sort of define this. So this is the magnetic force, and it'll have a magnitude and a direction, right? Its magnitude is QVB sine theta. Its direction is out the palm of your hand. Well, we'll talk about the direction with these pictures down here, okay? And then Q would be the charge that's moving inside a magnetic field. Force is the force that the charge experiences, okay? V is the velocity of the charge, all right? And B is the magnetic field that it's in, and that's your fingers. All right. Oh, by the way, the velocity would be your thumb. Like that. Okay. And then the sine of theta, or theta, is basically the angle between your thumb and your fingers, right? So it would be sort of, this angle in here, or this angle in there, right? Okay. Now, basically what's going on is, let's say I've got some magnetic field, and here the magnetic field is represented by just a single line, okay? But oftentimes a magnetic field would be, a field of lines. And so it's kind of nice. You actually point your fingers in the direction of that magnetic field. Then you've got some particles, zoom, that's sort of flying by that way, okay? Then you point your thumb in the direction of that particle, okay? And then all of a sudden, out the top of it, or out the palm of your hand, would then come that's the direction that this particle would get pushed, okay? Would get pushed. And your thumb, by the way, always remains flat, right? You never actually kind of move your thumb sort of towards the palm of your hand. You imagine your thumb and your palm of your hand remain a plane, okay? Like in these pictures here. Notice this guy's thumb isn't like pointed up like this in the direction of this vector, all right? Anyway, so that's kind of the idea there. This is the right-hand rule, so you would use this for positive particles, and this one over here is the left-hand rule. So right and left-hand rule, okay? And the left-hand you would use for negative particles, okay? And that's what we're looking at there. All right, so now what we can do is take a look at note in both of the above rules, the velocity is perpendicular to the force, all right? And this is this part here. And since the force is in the same direction as acceleration, therefore the velocity is perpendicular to the acceleration, okay? And when your velocity is perpendicular to the acceleration, I don't know if you remember, you actually have what's known as centripetal acceleration, and you have a circular path. And so what ends up happening here is all of your stuff ends up all of these particles that move in these paths end up moving in a circular path. Okay. All right. Here's an example. Let's go ahead and take a look at this. All right. All right. So we've got an example of a particle moving within a magnetic field. An electron accelerates from rest and in an easterly electric field, okay, through a potential difference of 46 volts. Oh, wait a minute. This stuff is from the last chapter, okay? The electricity chapter, okay? It then leaves the electric field and enters a big magnetic field, okay? That has this strength, okay? So this stuff here is magnetism. And now we want to describe in detail the path that the electron has in that magnetic field. All right. So I'm going to draw this, this one here. Basically, what's going on is we've got some sort of parallel plate system, I suppose. And we've got, this is east. And this is up, we'll say. All right. We've got some kind of parallel plate system. All right. And imagine this parallel plate system has like a little hole in it. Oh, so let me go ahead and do it like this. This is just like a little hole. And we got an electron sitting here, and it's accelerated east in this field. All right. Then we've got a magnetic field that's pointed down. B. All right. And basically what's going to end up happening is if I now take, this is an electron, so I'm going to use my left hand, okay, and I'm going to decide that this guy is, now on my left hand, what I'm doing is I'm now pointing my fingers in the direction of the magnetic field. So that would be like this way, down, this way, right? And then I'm pointing my thumb on my left hand in the direction of the velocity, which would be that way. So imagine, basically now the palm, my palm is sort of facing out towards you guys, okay? And as a result, that means the force, the magnetic force on this electron as it exits this electric field and enters this magnetic field, the magnetic force is out towards you guys, okay? Towards you guys. And so it starts to get pushed towards us, you guys, and me actually as well, towards us. So imagine now I'm moving my so as it gets pushed, then my thumb is still in the direction of the velocity of the electron. So what happens is my thumb is no longer pointed straight that way. It's starting to come out of the page as well. And basically what you can imagine is we've got sort of like a circle here. This is always better in 3D here. So, but we've got a circle that's sort of coming out at us, right? Now that circle that I've drawn there is down, right? But it's not supposed to be down. It's supposed to be like kind of out, towards us is what I'm trying to do. So now you basically have, at that point, a circle, and that's basically a detailed description of the path of the electron. as it has in the magnetic field. So I guess what we would say is the path, right, is circular, right, such that it's I suppose it's a horizontal circle, you know, um, rotating a horizontal circle, right, and it's rotating this direction, which would be, imagine now looking down from above, so looking down from this direction, it would be rotating clockwise. Clockwise as seen from above. Remember that this direction here is up. So, you know, imagine I'm in a lab here. I accelerate my electron out like this, and it starts to go back circular that way. And I'm sitting here looking at it with like a microscope from above. All right. That's what would actually happen to this electron, right? Question is now, the magic $1 million question is, what's the radius of this circle? Okay. So we've got this circle here now. All right. Now, obviously, what might happen is the electron might actually hit back here again, right? But let's just say, excuse me, let's just say that here, I'll do it like this. Let's just say that the magnetic field is sort of out here. So the thing has a little bit of chance to sort of go and do some circling. All right. Or, excuse me. Sorry, I got something a little caught in my throat. All right, so there we go. Question is what's the radius of this path? All right, so here's your classic formula. Remember, force magnetic is equal to QVB sine theta. Force magnetic is a circular centripetal force, right? The force magnetic is centripetal, right? Because a magnetic force is such that the acceleration and the velocity are always perpendicular, all right? Because of the shape of your hand, basically. Not really, but anyway, but because of the shape of your hand. Anyway, so the force magnetic is equal to the mass of the particle, right, times the acceleration, which is equal to QVB sine theta. And, well, the centripetal acceleration is equal to v squared over r. So we're going to go mv squared over r equals qvb sine theta. And here, this formula right here is essentially sort of like a go-to formula for all particles moving in a circular path in a magnetic field. And if you want to find the radius of this, then you just solve for r in this formula. And look how easy this is going to be. I'm going to basically pop r up there due to algebra. And so I'm going to say r is equal to the mass times v squared over qv b sine theta. And it turns out these v's cancel, right? Well, one of them does. One of these v's cancels with that. All right. And boom, there we have it. That's pretty spectacular. And so it turns out it's equal to the mass of the particle times its velocity tangential velocity, times the charge of that particle, divided by the charge of that particle, the strength of the field, and the sine of the angle. What angle is that? It's the angle of the velocity and the magnetic field here. Okay? All right? So that angle in this case is going to be 90 degrees because basically, look, at the beginning, my velocity was like this. Remember that was the velocity. Okay? And my field is down, right? And so what's the angle between east and down? The angle between east and down is 90 degrees, okay? And then later on, my velocity will be maybe like, not east, but south. And then it'll turn around and be west. And then it'll be north, right? But what's the angle between west and down? 90 degrees. North and down, 90 degrees. South and down, 90 degrees. So the direction between all of those cardinal directions, which is basically, remember, I've got a horizontal rotating circle, and down is 90 degrees. So this angle here will always be 90 degrees in this example, okay? Just in this example. There are other examples might not be 90 degrees, okay? And so we've got R, no, I already wrote that down. So basically we've got, that's what I'm going to, I want to find out the radius. So the mass of this particle, what is it? It's an electron. So that's 9.11 times 10 to the negative 31 kilograms times V. What's the velocity of this particle? Well, we don't know, but we can find out the velocity because, remember, it was accelerated from rest. That's here. Accelerated from rest in an easterly electric field through a potential difference of 46 volts. Oh, interesting. And so what we can do is we can say, since it was accelerated from rest, the change in electric potential energy should be equal to the loss of electric potential energy should be equal to the gain of kinetic energy. So I'm just going to go ahead and set those equal to each other, although there should be a negative sign there. But that's okay, because I'm just going to use this as a straight up velocity. And so my electric potential energy, if you remember correctly, is equal to the change in electric potential energy times the charge, right? The electric potential difference times the charge, and this is 1/2 mv squared, okay? And so this is basically how much electric potential energy right here that it gained, or that it had because it was over here. And all of that electric potential energy turned into kinetic, giving the mass of an electron here, this electron, into this velocity, right? So I'm going to have to solve for velocity here quickly. And so I'm going to do 2 delta VQ over M equals the velocity. And I'm going to have to square root that. That's from last chapter, the electromagnetism. Sorry, no, that was from the static electricity and electrostatics and electric field section. Okay. And so there, we've got all that stuff. So I'm going to go ahead and stick that stuff right in here, right over there. That's this area, because that's what I want to put there. All right. All right. Let me go ahead and get rid of that. And then I'm going to go ahead and divide it by the charge, which is 1.67 times 10 to the negative 19, if I remember correctly, times the field strength of the magnetic field, which is 0.2 Teslas, right? T stands for Teslas. That's the strength that's the unit given to magnetic fields. Apparently that guy, that crazy guy Tesla, ended up and doing a lot of stuff on magnetism. So he got that named after him. All right. And so there we go. We got 90 degrees over here, 90 degrees. All right. And over up in here goes the answer to this question. All right. So basically, why did I figure that? Well, the path. Why did I figure out the radius? Because I wanted to answer the question. Describe in detail the path that the electron has in the magnetic field. So I've basically described that path right here. And by the way, it has with a radius of basically this value. All right, where V is over there, right? Where V is the square root of 2 potential difference Q over M. All right, and there. That's kind of that one there. All right. Next section is the force of magnetics, not on particles, but on conductors themselves. So conductors make magnetic fields, and then they actually can be pushed around by magnetic fields that are made by other conductors. Oh my gosh, craziness. And so, right, this question was just simply about a particle in a magnetic field. Next section we'll be talking about what happens if an actual wire itself gets placed in a magnetic field. Okay? All right.